Thanks, Yin-Zhe, for today. We had a gap in our seminar series, so thanks, Yin-Zhe, for filling in the spot. And he'll be talking on the Hubble constant conundrum, a physical solution. Over to you.
Okay, thank you, Momita. Okay, so yeah, so it's a great pleasure to give this presentation. So basically, I'm to give a presentation in the SAAO, the South African Astronomy Observatory 200 Years Symposium. So basically, this was planned to be a preparation before this. So I would like to hear your advice on my presentation and what you think I should cover a bit more, or which I should cut down, or which I should emphasize. So your response is highly appreciated. So this project is about Hubble constant conundrum, which is the conundrum has been around for quite some time. I remember when I was a postdoc in Canada in UBC during 2011 to 2014, there was this problem already arise, but by then it was only 2 sigma. So people was not very serious about it. They think this will go away once the data is improved. But as you see from this diagram, which I show, if you see my cursor, can you see my mouse around here? You can see that at 2012, yeah, it was about 1 or 2 sigma, but by Wmap 9. But then when the Planck data released, the measurement between Planck and local measurement become even more severely different. So now basically the disagreement reached about 4 sigma or even 5 sigma, depends on what experiment you take into account. Okay, so what is this problem? First of all, I don't think I need to introduce to you in this group what is Hubble constant. So this is 1929, basically the Edwin Hubble using a very few data sets from the Cepheid, extrapolated the Hubble expansion law by just using this very scattered data set. You know, which I usually quoted as the nature always love the simplest law. So if you're unsure about whatever your data scaling law, your data is, give me a pencil and I'm going to draw a straight line for you. Okay, so that is the history part of the left-hand side. Let me update. Oh, by the way, this project I have been doing with my postdoc, Dr. Wei Ming. I think he's also in this Zoom, and also Professor He, who is a professor at TDD Institute in Shanghai. So we started this project from last summer, and now I think we almost finished it. I'm now in the 2nd round of review. Okay, so. Okay, so let me update you. This is the recent tension in the H0 measurement. So the early measurement are mainly from the cosmic microwave background radiation. So this is a Planck measurement, and if you're adding other ancillary data sets such as the BBN and the dark energy survey, you get almost the same value, except for the error bar will be affected. So, and the late measurement are from a variety of distant ladder experiments, including the shoes, the Cepheid distance plus distant ladder plus type 1a supernova, and plus others like different kinds of surface binding fluctuations, and also the tip of the red giant branch, etc. And also this very interesting time delay cosmography, something called helical. People later update to something called TD Cosmo, which also give a fairly high value of H0. So overall speaking, the early versus late is about 5 sigma by then, by now basically, which is quite a discriminant problem in astronomy and a need to pay attention to it. Okay, so before I present my idea to solve this, let me just briefly review with you about what are the local measurements and what are the CMB measurements and why they can measure H0 in such accuracy. So this is the local measurement, which is, as you can see pictorially, basically people find those Cepheid or other things. I mean, in this picture is most about Cepheid, and using the parallax in our own Milky Way to measure the distance to the Cepheid. And because Cepheid is a variable star, so one can use that basically the period of variation to basically calibrate the Cepheid, which in the other galaxy, look at the number 2 here, which in the other galaxy, which also hosts not just Cepheid, but also type 1a supernovae. So they can use that, they can use the bright period of that know the basically to know the brightness, and then use that brightness to calibrate those supernova which are in the other galaxies, in the same galaxies as the Cepheid. And then once these supernova are calibrated, they can measure the other supernova, which is in a further away galaxies, and therefore representing the cosmic expansion. So from these 19 calibrations, they can basically measure the luminosity distance and the redshift relation of these 300-ish supernova. Okay, so that is a local measurement. They build on distance ladder by using like the rung, like when you're climbing up on a ladder, you climb on different rungs of the ladder. Okay, so the other way is called gravitational strong lensing. If you can see my video, I think my video is played properly, right? Okay, so basically the strong lensing is where you have a background source, usually a variable quasar, and that will, because of the foreground dark matter halos, the light shedded from the quasar will be lensed and will be distorted and going past different light rays, and therefore forming such kind of interesting ring structure around it. We call Einstein ring, or different kind of images around it. So basically, if you measure the time delay delta t, which is basically the time arriving to your lens, and also, I mean, if you measure the left-hand side, and if you are able to measure the Fermat potential from the lens model delta phi, you're able to derive the middle quantity, which is a d delta t, which we call the time delay distance. And that time delay distance is inverse proportional to the H0 value, the Hubble parameter. So basically, measuring left-hand side and then measuring and modeling the Fermat potential, you derive the H0 value. Okay, so this is a time delay distance, and they give, as you can see, quite consistent result on the high value of H0, which is about 75, being consistent with each other. And the other big camp is about cosmic microwave background radiation. That is the fluctuation formed when the universe was only 380,000 years after the Big Bang. As you can see, this is the measurement from the Wmap satellite, and later on being updated by the Planck, and they see hot and cold spot fluctuations that form at a very early time of the universe. And the question to understand, the key thing to understand this is to understand why this hot spot can be there, why this hot and cold spot can be there, and how were they formed. They actually formed just like the normal acoustic wave. So suppose you have a quiet water pond, you drop a water stone, you drop a stone into the water pond, and that will make ripples. And those ripples will be propagated, but unfortunately in the universe, you have many stones at the random fluctuations in the universe, and that will form a cold and hot spot, being sort of a randomized structure in the microwave background radiation map. So basically, what we really see in this previous map is really this early hot and cold spot sort of fluctuations, and which really representing the acoustic oscillation at early universe. So the question now is, can we reconstruct that ripple, the ripple which I show in the video, by doing this? Okay, so the answer is yes, and you can actually quite easy to do it. In fact, there was an honor student working with me like 2 years ago on doing this, and he was so elevated. He said he was so exciting when he was able to reconstruct that ripple. So if you just cut around each of the hotspot, cut a little patch of a few degrees, and stack them all together, then you will get this, which is the upper panel here. So for Wmap, for each of the hotspot, you have a cold ring, and for cold map, basically for each of the cold spot, there's a hot ring, which is exactly what you see as the video shown in the ripple effect. And such kind of a feature of the hot spot cold ring, cold spot hot ring is also can be also seen in the Planck map if you just do that simple stacking exercise. So this is the intensity, and this is the polarization. Okay, so those are the binaural acoustic oscillation scale, which you see in the universe, which we usually call it the RS, which is a drag epoch, characterizing the distance where the sound wave can travel from the Big Bang to the 380,000 years, the decoupling time, where the photon completely become relics. So that RS is actually a fixed scale on the sky, which, as I said, you can quite easily to reconstruct it. And now basically the Planck measuring the microwave background power spectrum of it, the power spectrum of the microwave background, which is in a really, really high precision. If you see the right lower plot, the data with really tiny error bar really is really able to constrain the parameter in a high accuracy. So you can see that if you are able to constrain the power spectrum, you are able to actually constrain the angle, expanded angle, subtended angle for that RS over the cosmic distance. That cosmic distance is we call angular diameter distance. It's really the distance from the last scattering surface all the way to us, to the observer. Okay, so in fact, this L, this multiple moments, L is inverse proportional to that theta. So the first acoustic peak would represent the inverse of that theta value. So it's really measured to a high precision. So therefore, if you know what your RS is, and also know what is your theta, you can derive what is the dA, which is the angular diameter distance. And from there, you can measure the H0 value. Of course, it's model dependent, depends on various other parameters like omega m, omega lambda, etc. But this is the way you can derive the Hubble constant. And that gives you a low value of Hubble constant, which is 67 something plus minus 1, which make our discrepancy. Okay, so I think I made quite a lot for this introduction. So let me go straight to my solution. So first of all, when you face a conundrum of a two quite discrepant experiments, you can argue that CMB measurement might be wrong, or you can argue the local measurement might be wrong. I mean, but from my perspective, I think the CMB, the probability of this CMB measurement is wrong is quite low, because not only Planck recovered that low value, but also the ACT, the recent update from the Atacama Cosmology Telescope, also recovered a similar value of 67. So and they are complete independent group, and they do their pipeline, etc., completely independently. So to me, that CMB measurement is most likely to be correct. And then does that mean the local is wrong? Well, there are so many different local experiments, like the distant ladder, like the strong lens, etc., which also complementary to each other. So it's also hard to say that their measurement have some uncounted systematics, etc., is wrong. So okay, so now I'm going to scratch my head to think about new physics. Yes, I mean new physics. Not some hand-wavy phenomenological alternatives or any arbitrary parameterization, which could be produce a bewildering range of models. I think what we are doing, Professor He and myself and Dr. Dai is doing, is to do something based on holographic principle. Okay, so this may sound quite abstract, but really what that principle said is the information associated with a certain part of space may be represented by bits of the by the bits of information on the surface surrounding it. In the other words, the quantum state actually described by the variable on the surface. Okay, so in that sense, basically in 1990s, 't Hooft and also Susskind conjectured that the total degree of freedom by any effective scalar field in a ball with size L, this is a ball with size L, must be below the black hole entropy of the same size, which is a duality connecting the UV scale, which we write it here as a lambda square, a lambda to the cube, the energy fluctuation at the UV scale, with connecting this UV scale physics with the infrared scale, which is really a global scale. We call it L here. So this is the left-hand side is the total degree of freedom for any effective theory must be less than the size must be less than the information of the black hole, basically on the same size. That is something called duality relation, which is also quite deeply embedded in the current string theory. Okay, and later on in the later 1990s, this Cohen, Kaplan, and Nielsen basically further tightened up that they find if this equation is true, the previous this 't Hooft and Susskind conjecture is true, then it's implied that there are many states within box of L where the Schwarzschild radius is actually larger than L, in which case these states have been well collapsed and actually none exist, this quantum state. So to avoid this catastrophe, what they propose is a slightly tighter bound on the information by imposing the constraints on the infrared cutoff 1 over L that includes all of the states lying within the Schwarzschild radius. Maybe my language is a bit abstract to you, but trust me, if you take this equation, you find that actually the information is further reduced, and they only allow the states, the quantum state to exist in a tighter bond, which basically exclude those quantum states where their size of L is actually larger than the Schwarzschild radius. Okay, so let me just so in a word, holographic principle basically points to that in order for quantum state in box of L to exist and non-collapse, the short distance, which we call ultraviolet scale, is always connected to a long distance cutoff, infrared cutoff, due to the limit set by the formation of a black hole. It cannot be collapsed into a black hole. So in brief, we made two explicit assumptions. A is the holographic principle apply to the entire universe. Well, that sounds crazy, but to solve a crazy problem, you need to be a little bit crazy. So the box size L should be related to the horizon in cosmology. And the second is the dark energy is indeed the quantum fluctuation, quantum zero fluctuations, which is not some arbitrary phenomenological parameterization or any hand-wavy argument. So in our case, what we did is, I mean, this is Dr. Lee, which is my colleague before, and also myself and Professor Chen before I actually did my PhD, was actually parameterize this thing with such an equation DE, where we add in only one free parameter in this model, which is this parameter C. This is not speed of light. This is just a parameter we call C. So by saturating that bond, you can see saturating this coherence bond, we basically name such a quantum zero fluctuation energy. That scale with the infrared scale in the cosmology, which is really the future event horizon, because dark energy determines the future evolution of the universe. Okay, and the C is the only free parameter in this model by saturating that entropy bond. Okay. Okay, so, and then we apply this model to the real data to see whether these can really represent our universe. And first of all, I mean, we vary the value of C. I mean, this was the early paper of myself. This model, this holographic dark energy, can never recover lambda, which is in fact a generic feature comparing to the lambda CDM, because whatever the C you choose, the equation of state of dark energy always transiting, always evolving. There's no way you can recover an absolute -1 throughout the cosmic history. That is really the distinctive feature of this model. So it's not something which will never be distinguishable. It will be, as we will show in a minute, will be distinctive compared to the lambda CDM. So, so basically, if you choose a value of C equals to 0.5, you will going to get an equation of state, which is a transiting equation of state from greater than -1 to be a regime of less than -1. Yes, I know you might say this is crazy. Less than -1, it is some phantom. Yes, just let me do it. Okay, and I will show you that it will work. And basically, it will work to solve the problem. So as you can see that there are two other parameterization which I put in, which is the quite famous CPL parameterization with the free parameter W0 and WA. And the other one is a trans, which is basically a built-in trans dark energy equation of state model, which have all sorts of the other 4 parameters. But you can see ACE, holographic dark energy, with only one free parameter, has that generic transition of above -1 to below -1, actually representing the other models with more parameters. So this is more efficient. Okay, so basically, if you think about the previous question which I present to you, RS is relatively fixed. So theta is relatively fixed. So therefore, dA must be fixed. But however, we have to have a fixed angular diameter distance from the observer point of view, all the way up to the last scattering surface, but have to make the local H0 a bit higher than the CMB measurement, right? So you need the total angular diameter distance unchanged whereas the local acceleration a bit faster. So this is like the marathon runner. I mean, some of the people, I mean, run the marathon could keep a constant speed, but some people may run a little bit slow and have no feature of winning the prize at later time, but accelerated later, and therefore eventually could be getting the same point, getting the same distance at the same time, right? So in fact, this is what we are searching for. This transition from above -1, which makes the universe accelerated not that fast, but accelerated later, is a feature we are searching for. And holographic dark energy can beautifully provide such a feature. Okay, so if we just adding into Planck and BAO data and plus the Adam Rees 2019, we are going to constrain this. You can see we constrain this value of H0, which is quite well aligned with the 72 value, and with the preferred value of C, value of constant parameter C around 0.5. Okay, and this, the right-hand side plot is the plot of the Hubble parameter evolution as a function of Z for different BAO data, so which is showing in the table here, and also the Adam Rees local one, which is showing just right up here, which is the redshift 0 one. As you can see, the gray band is what lambda CDM would predict. So it's pretty well satisfied the BAO measurement, but on the local redshift 0 part is unable to recover that high value, so therefore discrepant. But whereas for our model, because of that interesting transition behavior, it can quite well going through these high redshift data, but also basically recover this local measurement on the high value of H0 due to the faster acceleration at later time for this. Okay, and if we basically, if we plot the probability of the, this is posterior distribution of the H0 by holographic dark energy and by lambda CDM and two other ancillary data set, ancillary models actually, you can see that for lambda CDM, whatever the value, whatever the data set you use, it always give you a 67, 68 H0, whereas for holographic dark energy, because of that generic behavior, it's not dictated by the data, it's a generic behavior. It always gives a quite high value of H0 of this, relatively equals to 72, okay? And you can see that these are the different results of the constraints with, the Planck plus BL plus Rees 2019. You see that lambda CDM almost unchanged, but holographic dark energy would give you a 73, which is pretty well consistent with this, and the chi-square is quite low, and delta AIC is the inference of this, okay, which is an inference parameter of this, and you can see that here. The beautiful thing is that it not only recover the local value of H0, but also can quite well of going through these BAO measurements at relatively high redshift. Okay. So the feature of holographic dark energy, in summary, it is a natural explanation from the holographic principle, as we see. It's just saturating that bond of entropy, adding one extra parameter of saturating the bond, then you're done, right? That model, there's no process of being contrived, and it's generically different from lambda CDM. So whatever value of C it is generically different. So therefore, it is very viable and falsifiable with future data. I mean, that is the exciting thing I find with this model. It's not like, oh, your future data set will be improved and therefore tightening up the constraint and therefore making your W to be as close as to -1, but always have a finite contour around -1. Therefore, the model will never be excluded. No, this one is falsifiable. And what I mean by falsifiable is the following. So for the future, I mean, actually very soon available DESI experiment, the dark energy spectroscopic instrument with 36 million galaxies in 4 years, that will produce us a lot of data from redshift 0 all the way up to redshift 1. And in particular, I mean, this will sample quite heavily on this range of difference between lambda CDM and holographic dark energy. And therefore, maybe our model will rule out, or maybe our model will be verified. Okay, so let's see in the next few years. And the other thing is the gravitational wave measurement with electromagnetic counterpart, and which are also able to constrain that H0 from completely different experiment. Okay, so I think I'm just leaving my talk here to leave you with this panel of the current discrepancy and our method of solving it. Thank you.
Thank you, Yin-Zhe, for the interesting talk. We can take some questions.
Very nice talk. If I understood you correctly, you've got this one free parameter C in your model, right? And you fix that by observations?
Yes, yes. Yes,
okay.
Yes.
What value do you have currently for that?
Sorry, I replay that again. Sorry for that. At the moment, my C value is about 0.5. Yeah.
Okay, thank you.
I mean, just by using the current data set, we find the C value to be 0.5. Yeah.
If you go to your next slide, I just want to know what the dashed lines are for the 1D. Is it for a different, including Rees et al. Data or something?
Yes. The dashed lines are, I think, yeah, whether or not you include Adam Rees 2019. So you can see that for HCE model, whether basically this blue curve, the blue solid curve and blue dashed curve, whether or not you impose Rees 2019, it always gives you a high valuation because that generic feature. Whereas for CPL parameterization or trans-DE, these are purely phenomenological parameterization of W of Z function, right? Yeah. So basically, if for those models, if you don't add Adam Rees 2019, it will not give you a higher value. Basically, you only need the data. You need the data to detect the valuation for those models. Whereas for holographic darkening, it's automatically produce your higher valuation. So that blue dash curve is not very far. I mean, it's from this blue solid curve.
Yeah. Okay. And just a quick question about, I think it was on your slide 3 where you had this 1D curves of H0 again. So I think the red and the blue both are by Suyu et al. Right? 2010, 2014. So do you know what is the difference between the data sets, what they have used? Like how is it? Because the blue is the one which is kind of deviating from the average of the others, right? So do you know what the data sets they were using?
Yeah, so actually I follow quite closely with this strong lensing experiment. So those are, I mean, those different measurements are actually from different samples of the quasar lens system. So they basically apply Hubble time and plus other telescope time to observe it. So for each of the quasar lens sample, there's a quasar and there's a multiple images, and what they measure is the time delay for each of the image. I mean, the in between of the images. Suppose you have 4 images, and then this and this would have a time delay. This and this would have a time delay. This and this would have it. So they would use 3 measurements to get the delta t and to pull out that H0. So certainly you have more images, you will have more time delay samples, and you're able to measure that H0 more precisely. So those are really from the quasar sample, which is a lens quasar sample from the optical observations. Yeah.
Okay, thank you.
And one of the major systematics for gravitational strong lensing is, as we just know recently, are 2 things. One is the line of sight mass concentration. So if you have a line of sight from the observer all the way up to quasar, and you have a line of sight different mass fluctuations, that will cause your time delay, which is not easy to incorporate in the Fermat potential side, right? Because Fermat potential is mostly about the potential in the lens, which is basically in the lensing galaxies. But if you have a line of sight mass fluctuation that is extended on a larger space, this is one thing. The other thing is even for the lens itself, you need even more precise modeling. And it looks like they may have a little bit problem of this. I'm not an expert. I can't question in full, but look like there are some other people argue that that may be a problem for the lens model. Yeah.
I mean, in this experiments, how do they measure the time delay?
They're able to measure it. Basically, they're able to measure it through the way of observing their light curve difference. So think about, I mean, let's see in the left-hand side movie, okay? Think about there's a variable quasar at the background level, right? The quasar will become bright, but dim, bright, dim, bright, dim, like a periodical quasar variation. And certainly on your camera, you can register the photons for each of the images. So, right? And therefore they will have a light curve basically captured by your cameras. And then those time delay are measured in the precision of days. So, so that's basically the delta T measurement. Okay, so they are able to do it. Yeah.
Okay, thank you.
Yeah, thank you, Yin-Zhe, for the talk.